Okay, so this is a video to go over what we call our parent functions. And because the name of this course, of course, is functions, we're going to be spending a lot of time analyzing and getting to know the behavior of different functions. Grade 9, you focus on the function, the line, or the linear relationships. In grade 10, you focused on quadratic relationships and also spent some time with linear relationships when you're doing your analytical geometry. And now we're going to be focused on quite a few different functions. The name of the course is functions, and we'll be getting to know probably, let's see, sine, cos, the exponential, these five. So we should get to know probably 8 functions very well before we finish this course, okay? As well as the transformations of those functions. That means changing the shape of those functions and seeing how they behave depending on what factors you multiply and or add, subtract from them to them. Either way, so what we have to do is we have to get to know what I call our base functions, but they're really called parent functions, okay? So the first one that we're going to go over is going to be one from grade 9. It's degree 1. That means the power on x is 1, okay? And that's the linear relationship. Now the most basic form of a line is y is equal to 1x or y is equal to x. Okay, in this case, the slope is 1, the y-intercept is 0. Okay, and so basically what I do to figure these things out is I take an individual value and I figure out f at -2, and I plug in a -2 and it's -2. Then I plug in for x -1, then I get -1. And here's 0, and I get 0, and then 1 and 2. And we know this line from our inverses, if you remember from our inverses, right? That this is your basic y equals x line. And the y equals x line is really important for inverses, okay, but it's also what we call a parent function. Excuse my connecting the dots, it's not perfect there. Okay, so that's what that graph of it looks like. A very simple 1-for-1 slope. A rise over run is 1/1. A simple process, okay? Special features associated with it? Not a lot. I mean, we've got the slope, okay, which is the rise over the run. We have a y-intercept, which is important, as well as x-intercepts. So we've got a y-intercept and an x-intercepts. But not all lines will have these. They generally tend to have y-intercepts, 1, and then 1 x-intercept, with the exception of vertical and horizontal lines. Okay, there doesn't generally tend to be any symmetry except along the actual line itself. So whatever the line is, they're symmetrical on both sides because there's no symmetry to it. But some lines will have symmetry. Horizontal lines will have symmetry to them, for example, in the x-axis, vertical lines in the y-axis. And if I was to basically reflect this in the y-axis, it would sort of appear over here. If I was to reflect this into the x-axis, it would appear over here. But either way, not really a lot of symmetrical values there, okay? But we did spend time with x-intercepts and y-intercepts, and maybe even use that information in our analytical geometry in grade 9 or grade 10. Okay, so that's the format y is equal to x. The domain for a line, as you can see, for the domain, the x values, it spans all x values in all directions because those arrows keep on going. So x is going to be a member of real numbers. Okay, I'm not going to put the domain there because for a lot of them we have restrictions on the domain, and if I have them up here it'll be too scrunched. Same idea for the range. It goes upwards, continues upwards diagonally, and continues downwards diagonally, so all the positive infinity to negative infinity. So we go y-er, or y is a member of real numbers, or if you want to use proper everyday language, x can be any value, y can be any value, and there's no restriction. Okay, in general we'll look at this a little bit later on. Okay, once we know a little bit, we may want to come back here once we're later on through the unit, and we know about our transformation as well as our translation factors and the roles that they play. But right now we're looking at the parent functions. Okay, another one that we know really well is y is equal to f at x, or f at x is y is equal to x squared, or f at x is equal to x squared. In this case, I plug in a -2 to x squared. Using brackets, -2 squared is going to give me a +4. -1 squared is going to give me a +1. 0 squared, of course, is a 0. 1 squared is 1. 2 squared is 4. And we get this sort of turnaround point, 4, 1, 0, 1, 4, as we go from left to right. So as we go -2, -1, 0, 1, 2, again, we get larger and larger down, or sorry, smaller and smaller down to a value, and then we increase by roughly the same rate. Okay, so we've got 0, 0, a very important point. We've got 1, 1, or sorry, -1, 1, 1, 1, 2, 4, -2, 4, and then I guess we could keep on going and go all the way up to 9, forming this nice parabolic shape to it. Okay? There is a special feature, something called the vertex. Okay? We used to know it as HK, okay, where H was a translation horizontally and K was a translation vertically. Now we're going to know it as something called DC, and you're like, well, why are we just stay with me on that. We'll figure it out. Don't worry. We'll learn about that together in the coming days, okay, or coming lessons. Okay, so the vertex is a key point. Is it symmetrical? It does have an axis of symmetry. At the vertex, and it's always x equals, it's a vertical line, so there's a vertical axis of symmetry. I'm just going to put a little bit offset here, just so you can see it very well. Okay, and it's that x is equal to k, or with our new notation, x is equal to c. In this case, x is equal to 0, or the y-axis is the line of symmetry for this basic parent function. Okay, so again, we want to get to know those points pretty darn well. Okay, just so we can be sure to sketch these functions and then transform them afterwards. For the domain, if you notice the parabola goes to all x values, it does kind of tend to sort of seem like it's going to just stop off at an x value, but it does keep on going upwards and upwards and upwards. This goes upwards and upwards and upwards as it goes outwards. So it'll continue to go outwards and outwards and outwards. Key feature is if I was to put in an x value of 10, 10 squared would be 100, but it still is allowed. All x values positive and all x values negative are perfectly allowed to be plugged into that equation, and it will just continue to get larger and larger. In fact, the y values will get very large. The value of the function will get very large. So we go x is a member of real numbers. There's no real restrictions on the x values, but the y value, there is a restriction. The vertex creates that restriction. So the restriction that exists here is we have a boundary right here, and the boundary is at the vertex. So in this case, my range has a restriction. In this case, for the most basic y equals x squared, it's going to have a restriction at 0, okay? And then after that, y is really a member of real numbers. I guess I should slide that over, yeah. 0, y is a member of real numbers. And we know, of course, that it can be 0 or larger in this case, so greater than or equal to 0, and y is equal to x squared. However, in general, we will maybe even remember from last year that this value is actually, in general, as its y is going to be greater than or equal to, or less than or equal to, if we reflect the parabola, okay, and it's going to be your k value, okay, or a little bit later on, instead of using k, we actually use the k for something else, okay, it's going to be a c value, okay, for this year, and that's for this year. In general, there's nothing really to glean from any of the values there, because every quadratic parabola is just going to be x such that x is a member of real numbers. So there's really nothing crazy that's associated with that in all parabolas. Okay, another example of a function. This is a new one for you, one that you haven't seen before, but it is very closely related to the root function, and that is the very related to the quadratic function where you square things. So this is a root function, which is the opposite. Oh, by the way, for y equals x squared, that's a degree of 2. This is a degree of opposite to 2, so it's a degree of 1/2. Most people don't know that for the square root, but a square root is a fraction. We'll learn that when we learn our exponent laws in our exponential functions unit. We'll learn a little bit more about that. So I'll take the same values. I'm going to take the 0, okay, because the square root of 0 is 0. That's easy, right? You take a 0, you plug it in there, square root of 0 is 0. You take a 1, and you plug it in. And now here it's assuming just a positive, Okay, it's not a plus or minus because we're not doing the square rooting. We don't have to consider both the positive and the negative inversion. This is just a positive, so as a result, the square root of 1 is only a positive 1. Okay, and then 4. Okay, and the reason why I picked 4 for x is because it's a nice even number when we square root it. Okay, if I picked a 2, the square root of 2 is 1.41, which is fine. But if we want to do some transformations, we want to pick nice round whole integer numbers to do our transformation. So it's good to know some key points as the 4, square root of 4 is 2. Okay, so you take the 4, you plug it in here, square root of 4 is 2. Notice how I don't have any negatives, like -1 and -4, okay, because they will not exist. So I really only have 3 specific points that are useful. I could continue to go onwards. I would put a 9 here and make the square root of 9 a 3. But in reality, it's just sort of simpler for us to keep it to nice, perfect squares. Okay, 4, 1, and strangely enough, 0. So here's 1.00. Here's the other point, 1, 1. And here's the other point, 4, 2. And what you're going to see is it's sort of like an upside down check mark sort of looking thing. Okay? But we got to get to know these points really well so we can sketch them quickly. Okay? Now they sort of have a vertex, or like an ending point, if you will. Okay? Rather than turning around like a vertex does, it's not really a vertex, but it is a very, very key point. Okay? And that vertex, strangely enough, is also D, C. Okay? So the same way, we don't have an H and a K, we don't use an H and a K for quadratics in grade 11 because, well, it's a long story as to why, but the K has already sort of been used up way back when we're looking at a lot of physics and mathematical principles. We use the constant multiplier like a slope as a K. And so as a result of it, for all the things like spring constants and all sorts of constants that are created, for all kinds of things that are consistent, we use the letter K. So for whatever reason, the curriculum uses H and K in grade 10, but they really should use other letters. In this case, we picked D and C. It doesn't really matter what it is, although the C is a bit more consistent for some respects. But either way, so we use the D and C. D and C, this is an X coordinate. This is a Y coordinate. This is a horizontal transformation factor, just like, or translation factor, just like H just moves side to side. And C is like K, and then it moves up and down. So that's sort of our vertex in there. And the vertex is pretty important. It is not, or it shows no symmetry on the X or the Y axis. Interestingly enough, it does have some beautiful symmetry along the Y equals X line. Okay, and I'll show you that I showed you that when I showed you what an inverse was. You saw what a root function looked like there. Okay, so, but we're not going to get into all the symmetries that are associated with it, because then we can have the Y equals negative X line and so on and so forth. But there is some nice symmetry along that line if you have the full function. But that's neither here nor there. Okay, so anyway, so these 3 points are what are essential. Again, we kind of have a vertex. This is like it's not really a vertex, but it's kind of a vertex, certainly an important point. Now, what's going to be important here is we are going to have a restriction on X, and we will have a restriction on Y. So the parabola, which is kind of what the shape is, it's like a sideways parabola. This parabola, okay, that you see over here, okay, seems to basically go off upwards and to the right. So as a check mark, it goes up and to the right, okay? So at this particular point of inflection right here, or sorry, point of inflection, at this particular point of importance, we actually have 2 boundaries that exist. So the X values don't go into the negatives, and we know they can't go into the negatives because you can't put a negative in this particular function. So we say that X has got a specific relationship with 0. Okay, you can't put anything smaller than a 0. So X is greater than or equal to 0. Okay, it's got to be 0 or bigger when you put it in there, at least for this basic parent function. For the Y value, the same idea. The Y value stops at 0, the lowest, and then it goes upwards. So again, Y also has an intimate relationship with 0, and then it's greater than or equal to 0. Now, strangely enough, the range for Y equals X squared, and the range for Y is equal to root X is exactly the same. Okay, it just so happens that we also put a restriction on the domain when we have this root function. Okay, because only specific x values are allowed underneath the hood of that square root sign. Okay, in general, we're going to go a little bit further with this. Okay, because this is a new function, we're going to get used to the transformations, and we'll learn about those. So you may want to come back and update those so you can use this as sort of a study sheet. But we definitely need to get to know these numbers, these 3 points, and this overall shape and behavior to it. Okay, the next function that we're going to look at, okay, is what's called the reciprocal function. It's also a new function, although it really relates to our rational expressions unit that we either are doing or have done. In this case, for our course, have done. And so when we plug it into here, if you'll notice, it's y is equal to 1 over x, or f of x is equal to 1 over x. Okay, so whatever value I put in for x, it's actually sliding down in the denominator. Okay, so when I take this -2 and I put it down in the denominator here, it actually becomes 1 over, or -1 over 2, or -0.5. If I put in a -1, it becomes 1 over -1, or just -1. If I put in the 0, this does not exist, right? We can't divide by 0. So that's like a hole or something weird's going on here. If we put in a 1, okay, 1 over 1 is 1. If we put in a 2, 1 over 2 is 1/2, or 0.5, okay? Now you may ask yourself, wow, I don't really know what's going on here, but it does have this interesting idea. It's got 1, 1, and -1, -1. Now if you put in a 2, all the way over to here at 2, it actually becomes 1/2, which is littler. And if you put in a 3, it becomes 1/3. And if you put in a 4, it becomes 1/4. And if you put in a 5, it becomes 1/5. So what's going to happen is this line is going to kind of go really close to, but never quite touch that x-axis. And at the same time, what's really interesting, although we're probably never going to sub in values like this, but if I was to take a value in here, let's say 0.5, if I put a 0.5 in there, 1 divided by 0.5, or 1 divided by 1/2 is actually 2. If I put in 1/10 here, 1 divided by 1/10 is actually 10. So what happens is in this area between 0 and 1, it actually takes off super de-duper fast, and then comes really close to, but doesn't quite get to, that y-axis. Okay, so it comes really close to x-axis, but doesn't get there. It comes really close to the y-axis, but doesn't get there. The same thing happens in the negative side with the numbers. And so it forms this really sort of cool looking function there. First of all, it's a piecewise function. It's broken into 2 pieces. And it's broken up by this x value. This x value that breaks it up is something that the line comes close to but never quite gets to. X is equal to, x is equal to 0. It's called an asymptote. Okay? And the asymptote, in this case, there's actually 2 asymptotes, are at x is equal to 0, okay, or the x-axis, the y-axis, okay? And then there's also an asymptote, let me just turn it diagonally here, there's also an asymptote that goes this way that it never quite gets to, okay, at y is equal to 0. And so we have another asymptote at y is equal to 0, or the x-axis. And so what happens is we get these, and we use these as dotted lines, dot, 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 dot. Okay, and these are actually boundaries between the 2 pieces of the function, between the negative side and the positive side of the function. And they do kind of behave a little bit differently. One of them, when it gets close to that line, takes off positive. One of them takes off negative. Positive infinity, negative infinity, as it goes close to that line. As it goes away from the line, it goes down to 0, and it goes down to 0. Okay, so it's got some really interesting ideas happening there. Okay, there's also a symmetry in the y equals x line. And what that means is, if you took a line and drew it just like that, and you flipped it on itself and looked in the mirror like we did for our inverse, the inverse of 1 is 1 over y, the inverse of y is equal to 1 over x. Maybe I'll do it over here. Okay, remember we have f at x is equal to 1 over x. Remember, to find the equation of our inverse, we go y is equal to 1 over x remember, for the inverse, x becomes y and y becomes x. So I go x is equal to 1 over y. And then I go ahead and I multiply both sides by y to get rid of that fraction y. Boom, boom, goes there. And I have yx is equal to 1. And then I divide both sides by x. And I get y is equal to 1 over x. So your inverse, so y is equal to f at x. So f at x and f minus 1 at x are the same function. So it's really cool because it's a symmetry in the y equals x line. Okay, and that's kind of a cool thing that's happening there. Now, for the restrictions on the domain, we really have every x value that's possible. We go to positive infinity, we go to negative infinity for x, but the one value we're not allowed is x cannot equal 0. Cannot equal 0. Okay, and the same thing for the y value. We also have a y value. See right here, it takes off to go towards positive infinity for y, goes towards negative infinity for y, but it never quite gets to the 0. So in this case, y cannot equal to 0. And it's a little bit more peculiar why it's y cannot equal 0, because we know that we can not put a 0 in for x. That's kind of a no-brainer. But what happens is, as we get bigger and bigger and bigger and bigger and bigger and bigger and bigger for this value, 1 over 10, 1 over 100, 1 over a million, this whole value of the function, this whole fraction starts getting closer and closer and closer to 0. 1 over a billion, 1 over a trillion, 1 over infinity actually is 0. But we never get to infinity, so we really can't get to 0. So that's the whole idea. We approach 0, but y can't quite be 0. The same thing for the negative. Okay, 1 over negative 10, 1 over negative 100, 1 over negative a million, 1 over negative a billion is going to be negative, but still getting closer and closer and closer to 0, just from the other side. And that's what happens. As we get bigger and bigger and bigger and bigger and bigger x values, it gets closer and closer to the 0 on the negative side of the x-axis. On the positive side of the x-axis, it gets closer and closer to 0. It's a little bit tougher to see that one. And again, we'll wait on the in general. The last function that we have to get to know pretty well is something called the absolute value function. It's just like these straight little brackety things. But basically what it does is I take the value that I sub in there, and I keep it the same number part, but I make the sign positive no matter what. So if I put a 2 in here, the absolute value of 2 is positive 2. The absolute value of positive 1 is positive 1. The absolute value of 0 is 0. So the number parts aren't changing, but it has to end up positive. The absolute value of negative 1, the number part stays the same, 1, but it becomes positive 1. Okay? Negative 2, number part stays the same, but it becomes positive 2. Okay, so I guess I could put pluses in front of that. Okay? And so the absolute value function looks a lot like a parabola, but a really sort of rigid, straight parabola. And it looks sort of like this. And of course, it takes off in the other direction. So really, everything that we know about a parabola or a quadratic, okay, more appropriately a quadratic parabola, okay, it has a vertex. Okay, I'm not going to call it HK, but it is going to be D and C. Okay, it has symmetry. Okay, so it's got an axis of symmetry, or it's symmetrical about the y-axis, or x is equal to 0. Okay, or in general, x is equal to D. All right, and so it's the same sort of deal. If you look at a parabola and you look at, it's difficult to put because the parabola's up here, but I don't know if I folded it over or something like that. Okay, if you look at a parabola and you look at this guy, they're basically the same deal, right? So my domain, x goes off in this direction, x goes off in this direction. So x can be anything, really. And the way I write x can be anything is x is a member of real numbers. For the range, it's got that turnaround point. See right here at that sort of vertex idea? Okay, it basically stops at that value. So in this case, y and 0 have a relationship. Otherwise, y is a member of real numbers because we can connect those dots, and that any value is allowed as long as we follow this restriction. But we know in here y has got to be greater than or equal to 0. Okay, and any of the in general stuff, I'll leave you guys to that so you can understand it a little bit better. But any of the in general stuff is going to be something that you'll ascertain as we get more and more used to these particular expressions. Okay, and the transformations that go along with those, and that's to come. All right, so there's our parent functions. Now the next thing we're going to do is an inverse. Okay, and sometimes I teach the inverse before, sometimes I teach it afterwards. For this particular class, I'm going to be teaching it afterwards, so you don't know what an inverse is, and you don't know what I did over there, but you'll be able to come back to that. In addition, what I will do is I'll scan these guys. It's not a beautiful, beautiful copy, but it's kind of difficult to see them in the video all together, so what I'll do is I'll scan that and include that in our notes, so you have a nice, pretty version of our notes. Okay?